The law of refraction. The refraction of light happens as we go from one medium to another because the index of refraction changes from one medium to another. Effectively, it changes its speed. Now, when light is traveling through air, it's traveling nearly at about 3 times 10 to the 8 meters per second. When it enters glass, it travels at a much slower velocity. And as a result, this ends up changing the way that the wave fronts will propagate. Now, if the light is just entering the new medium head on, basically at a normal angle, all the wave front will enter the new medium, the slower medium, all at once. However, if it's entering the medium at some angle, part of the wavefront will enter first. It will slow down more than the other part of the wavefront, and this will refract the light. It will change the direction at which the light is propagating. It will bend the light, if you will. And here we can see an example of refraction taking place in an aquarium. This is actually producing 2 images of the same goldfish. Again, as it goes from water to air, it's changing its speed, and therefore it's changing its direction. And this actually produces 2 separate images. Let's take a look at light traveling from air to glass. Here we see the incident ray hitting the surface of the glass and some of the light being reflected. And of course, we know that the angle of incidence is equal to the angle of reflection. But a more complicated relationship is the relationship between the refracted ray and the incident ray. We notice that as we go from the faster medium, in this case air has an index of refraction of about 1, we're traveling about 3 times 10 to the 8 meters per second, that when we enter the glass, we're now traveling at a slower speed, about 2/3 the same speed. And the refracted ray has a smaller angle than the incident ray. So we can say here that θ2 is going to be less than θ1, even though the speed in 1 is greater than the speed in 2. Now here's an actual picture of light traveling into lucite and reflecting at different interfaces. The first ray traveling through the air suddenly enters the lucite, which has about the same index of refraction as glass, about 1.5. So we notice that it now has a slightly different trajectory than it did before. Now remember, we define the angle of incidence and the angle of reflection with respect to the normal of the surface, the normal of the interface. So clearly we can see that this angle here, θ1, is greater than θ2. Okay? And of course, some of the light reflects off this first interface. So we get a reflected beam right here, hits the bottom of the lucite, reflects off of that, okay? And then comes to a new interface. Now we have the reverse happen. We see that in this case, θ2 is less than θ1, okay? And θ2 represents the angle of incidence, where θ1 now represents the angle of refraction. So again, we see the same thing. When we're going through or propagating through a faster medium like air, the angle is larger. As we enter a slower medium, such as lucite, such as glass, even water, the angle becomes smaller. Now we can see why exactly this happens. And this leads us to what we know as Snell's law. Instead of looking at the rays, so in this case, we can clearly see the rays. We have one ray right here, okay? That's the incident ray. We have our other ray right here. This is the refracted ray. We're going to look at the wave fronts, which we know are perpendicular to the rays. In fact, the rays are basically representing the direction that the wave fronts are going to move. So as these wave fronts are getting closer and closer to our interface, closer and closer to the glass, the lucite, or whatever, we see that this part right here, I'm going to circle this for you so you can actually see this. this part right here is going to enter first. So it is going to slow down before the center enters. And in the next wavefront ahead, this part enters, then this part enters, so on and so forth. So really what's happening here is this part of the wavefront has slowed down. This part of the wavefront slows down. This part of the wavefront slows down. And this part of the wavefront slows down, okay? The last part of the wavefront to slow down is over here. So what happens is this part, okay, slows down and allows this end to catch up with it, or in fact, get ahead of it a little bit. Well, catch up with it's probably a better way of thinking about this. And we notice this changes the orientation of the wavefronts. We have gone from a wavefront, which is essentially going in this direction right here, to a new wavefront, which is now going in this direction right here. And again, that we can clearly see this new wavefront, if we represent it with a ray, is traveling in this direction. It was traveling in this direction originally. Okay, so hopefully that gives you a good idea of how entering a medium with a different index of refraction, with a different speed, is going to change the direction that a ray is going to be pointing. The ray, of course, is an approximation. It's essentially saying this is the direction that the wavefronts are going, because it's the wavefronts that are affected by the speed of the wave. The wavefronts represent perhaps peaks or valleys in the electric or magnetic field as they're propagating through a medium. And again, here we can see the same thing, just taking away the wavefronts. We enter with a larger angle, theta 1, that's our angle of incidence, and we enter the glass and propagate through the glass with a smaller angle, theta 2. And this is proportional. The difference in speed, if we look at the geometry here, is going to be proportional to the sine of theta 1 divided by the sine of theta 2. Okay? Now, again, if we reverse this, if we go from glass to air, our expectation is we're going from a slower medium, okay, where theta 1 is smaller, to a faster medium, theta 2. Again, the ratio of the sine of the angles is proportional to the ratio of the velocities. And, well, that makes it proportional to the indices of refraction. And our index of refraction is c, 3 times 10 to the 8 meters per second, divided by the speed of the wave through the transparent medium. And this leads to, let me jump ahead just a little bit. This leads to what we know as Snell's law. N1 times sine theta 1 is equal to N2 sine theta 2. Remember, N1 is inversely proportional to the velocity in medium 1. N2 is inversely proportional to the velocity in medium 2. So Snell's law basically allows us to relate the speed of the waves to the index of refraction, which is inversely related to how fast the waves are propagating. Okay, so a little more complicated than what we had for the law of reflection. In the law of reflection, we had the angle of incidence is equal to the angle of reflection. Here we have the index of refraction times the sine of the angles being equal or being proportional. So let's do a little calculation right here and try to calculate what the angle change would be going from air to crown glass having an index of refraction of 1.52. And let's set the incident angle at 30 degrees. So we first of all start with Snell's law. N1 sine theta 1 is equal to N2 sine theta 2. We want to solve for what the angle of refraction is. Okay, so I'm going to try to solve for theta 2 here. I put sine theta 2 onto the left side. I divide both sides, in this case, by n2. Move n1 divided by n2, sine theta 1 to the right. And then in order to get rid of sine, okay, in order to get rid of the sine function, I've got to take the inverse of the sine function. Basically, I'm going to take the arc sine on this side, and I'm going to take the arc sine or inverse sine on the other side. The inverse or arc sine is going to get rid of the sine on the left-hand side, and we're finally left with this expression right here. So the angle of refraction is equal to the inverse sine of the ratio of n1 divided by n2 times sine of the angle of incidence. So here I plug in my numbers. 1 divided by 1.52 is the index of refraction of air divided by the index of refraction of crown glass. I picked a really easy angle for myself. Angle of incidence of 30 degrees. I knew I was going to take the sine of that. That is 1/2. 1 divided by 1.52 is 0.66. So now I have the inverse sine of 0.33, and that gives me an angle of 19.3 degrees. And as expected, I went from 30 degrees to a smaller angle, okay, to a smaller angle of 19.3 degrees. Okay, so as the wave slows down, again, the last edge of the wave front to enter is able to catch up with the other, and that changes the angle a little bit, gets the angle going a little bit closer to the normal. And again, that is related by Snell's law. Let's do another one. Basically, all the math is going to be the same, except we're going to change the index of refraction for our second medium from 1.52 crown glass to diamond. Diamond has a very, very large index of refraction. Okay, so the only thing that's going to change in this case is going to be this ratio right here. Everything else is the same. I'm calculating the angle of refraction by using the arc sine. Okay, we still have this ratio between the two indices of refraction, and we multiply again by sine 30 degrees. So now this time we get an even smaller angle. Not surprising. We're going to an even higher index of refraction. So now we're going from 30 degrees to 11.9 degrees. So that's how you apply Snell's law. You can even do it for going from higher index of refraction to lower index of refraction. So for instance, flint glass to air, okay? Actually, it's not flint glass. This is crown glass. It's 1.52. In any case, again, we apply Snell's law. Again, we're going to pretty much get to the same point. Here's Snell's law. We're going to be solving for the angle of refraction. So we're going to put theta 2 on the left-hand side. That requires us to take the arc sine of both sides. And now our ratio here, n1 over n2, is greater than 1. Okay, you get 1.52. The sine of 30 degrees is 0.5. So the arc sine of 0.76 is 49.5 degrees. And clearly you can see here, this 30-degree angle is smaller than this 49.5 degree angle. Okay? Again, the math is really not too much of a problem. I think the biggest challenge that anybody faces with this is, you having to use an inverse trig function. That's not a huge deal. Okay, you're just taking the inverse sine on both sides in order to solve for the angle. Now, the other thing that happens when we pass from one medium to the other is that essentially, if we think about what's happening microscopically, the atoms, the electrons in the atoms, the electrons in the molecules are acting like little oscillators, okay? And they are basically oscillating at the same frequency as the electromagnetic wave that's passing through the medium. So really, we're stuck with whatever frequency we started out with the light. This is very, very important. The frequency of the light is constant, regardless of what the index of refraction is. The frequency doesn't change. The frequency remains constant. There's nu for frequency. If you're more comfortable using F, that's fine too. Generally, in upper level courses, we like to use nu more than we like to use F. But again, if we think about this, we know that the speed of a wave is equal to the wavelength times the frequency. So if we're holding the frequency constant, if the frequency doesn't change, and the speed is changing, that only means that the wavelength must also change. So if you're going from a slower medium to a faster medium, our expectation is the wavelength would get bigger, okay? It's got to cover more ground, speeding up. Wavelength has to stretch out to cover the same amount of ground for the same rate of oscillation. If, however, going in a slower medium, the wavelength is going to get smaller. So here we see two media here, okay? Perhaps V1 represents the velocity of light through air, around 3 times 10 to the 8 meters per second. Maybe V2 represents the velocity traveling through glass. Notice what happens. We can think about this conceptually first, and then talk a little bit about the math behind it. As these wave fronts come through, okay, they reach this interface. They reach the interface between the air and the glass, and now all of a sudden they're going slower. The wave fronts are still the same number per second. Frequency is the same. What that means is, as the wave fronts have to slow down, they begin to bunch together, right? And that means that the wavelength must also be getting smaller. So generally what happens is the wavelength of light in a vacuum is different than the wavelength that that same color of light, that same frequency of light is going to have in some medium with an index of refraction greater than 1. Okay? So very simply, if you were to take, I don't know, 500 nanometer light, okay? Sort of greenish light, okay? 500 nanometer light. And you're to go from air to glass, okay? That's basically dividing the 500 by 1.5. Ooh, I have to think about this. Essentially that fraction is 2/3. So 2/3 times 500 gives you 333. Okay, I was able to do that in my head. So again, if this is green light, 500 nanometers, we go into our glass, index of refraction 1.5, smaller wavelength. Okay, and think about this, not in terms of the way we were doing it before with rays. Think about this in terms of the wave fronts and how they bunch up. And again, here is our equation for the speed of a wave. Again, I prefer looking at like this, wavelength times frequency, nu, instead of F. But again, if the frequency is held constant, then the ratio of wavelengths is going to be proportional to the ratio of velocities, air to glass. Velocity is inversely proportional to the index of refraction. So lambda 1, the wavelength in air, divided by lambda 2, the wavelength in glass, is equal to N2, the refractive index in glass, divided by N1, the refractive index in air. And again, here's an example. Let's take, in this case, I'm going to start with red light. This is at 650 nanometers. And we're going to go from our air. Okay. Basically, we now enter the glass. Notice that I take 1 divided by 1.52. The new wavelength is 428 nanometers. So two things really happen to light as it passes from one medium to another. First of all, the angle will change unless it's normal, okay? If it's heading straight through, then it's going to have an angle of refraction of 0. Again, by Snell's law, the sign of 0 is going to be 0. So both sides of Snell's equation have to be 0. The angle of incidence is 0. But for a non-zero value, okay, going from a faster medium to a slower medium, the angle of refraction is going to be less than the angle of incidence, but also the wavelength in the refractive medium is going to be less than the wavelength in the faster medium. So angle changes, the light changes direction, it bends, refraction, but the wavelength also changes. Here's an interesting phenomena that we see when we watch air on hot surfaces. Again, I think the index of refraction for air is really, really small. It's 1.0003 or something like that. So you wouldn't think that a slight change in the density of the air would have very much effect on how the air is bending the light, how the air is bending or refracting the light that we see. However, at a steep enough angle where we see an effect called a mirage. And a mirage is not a hallucination. A mirage is an optical illusion. And with a mirage, we see hot surfaces that appear to be wet because, like a surface of water, they're going to strongly reflect the light. So it almost looks like here that when I'm looking at this, the headlights, okay, bounce off the surface, okay? You can see the headlights here, and we can see the headlights here, you know, bouncing off the surface. And it appears that the headlights are reflecting off of what essentially is water, okay? However, what's really happening here is we have this hot film of air, which is sitting on top of the road surface being asphalt, absorbs a lot of the energy from the sun, and that air is going to be much lower density than the air above it. So essentially, when I'm looking at this truck, I have cold air above, I have hot air near the surface, and the light is going to refract. It's going to bend toward the colder air where the density is higher and where the index of refraction is higher. Let's go back to our other example right here, okay? We see here that the incident light bends, okay, bends more toward the higher index material, okay? Probably not the best explanation for what's going on right here, but think about it this way, that light tends to refract or bend toward the material where it's going to propagate slower, okay? So if we think about this right here, this mirage forms as the light bends upward, and we get two images from the headlights. We get the light that directly comes to us, and we get the light that bends down and then comes to us, producing that reflected and distorted image down there. Here's a better example of how this might look. So for instance, if you're looking at an object and the angle with respect to the ground is very, very shallow, okay? the light is going to take two paths. It's going to take this path right here, and it's going to take the direct path to our eyes. So what we will see is from the blue path, we get an image of this object up here, the cactus. But if we follow the red path, we see that it bends. It bends up toward the cold air. It's trying to get to the slower medium because light bends toward the medium with a higher index of refraction. And as it does so, our eyes, our brain, thinks that the light is actually coming from this inverted cactus, which basically becomes an image. So it's not a reflection that's taking place here. It's not that the image of the cactus is being reflected off of, like, say, the surface of a lake. It's that the light is being refracted so much that it appears to be reflected off of a reflective surface that's not really there. And that, again, is how a mirage works.